Hi. To set the scene, I would like you to start off to imagine the person that's sitting right next to you, or that would be sitting right next to you if we were at the University of Sao Paulo. And furthermore, I would like you to imagine how that person is set up right now, maybe at home, doing home office, or at a proper office. And if you don't have a picture in mind, I would like to help you out a bit. It might look like this, or comfy on the sofa, or could also look like this in a more proper office setup. Well, anyway, I'm happy to have the opportunity to introduce you to Asymptotics for Push on the Complete Graph, a paper that's joint work with Rami Daknama and Konstantinos Panagiotou. And in this talk, I will introduce you to the concept of randomized rumor spreading, and I will show you one truly astounding behavior that this model has to offer. And to that end, we will proceed as follows. First of all, I will give you a intuitive understanding of randomized rumor spreading. Then I will define it more rigorously as push on the complete graph. Secondly, we will gain an intuitive understanding of randomized rumor spreading by relating it to two well-known problems, namely the birthday paradox and the coupon collectors problem. After that, we will see some related literature. And finally, we will get to our main result, and we will see the gems that randomized rumor spreading offers. Going forward, we will start with a small example. So this is Alice, and these are her friends. Alice has some kind of information. We will say Alice is informed. And her friends don't have the information, so we will say her friends are uninformed. And Alice wants to pass the information that she has and that her friends don't have. She wants to pass the information to all her friends. So to that end, she just randomly chooses one of her friends, maybe that one. They have a quick talk, they chat a bit, and Alice tells the friend the information. We might say Alice pushes the information to a friend, and then the friend is also informed. But Alice wants to spread the information to all her friends, and she also enlists the friend that she initially called to help her. So now both of them select randomly another friend, and they call them, they push the information along, and now we have 4 people informed. And they go on to spread the information further. And here we see some assumptions that we make. One assumption is, or the main assumption is, that we proceed in synchronous rounds. So we have some ticks, and on all of these ticks, those pushes happens from all informed people. They randomly choose a person, and they push the information along. And they don't stop until everyone is informed. So they randomly choose a few more, and now everyone knows the information. Alice is happy. But this is quite, well, an so-called the phone call model. We want to have this more rigorously on a graph. So we have here the complete graph on n nodes. That's denoted by the symbol kn. As the vertex set, we have the nodes or the numbers from 1 to n, and we have all possible edges present. So in the bottom here, you see the complete graph on 6 nodes. And then we start by labeling one vertex as informed. So that's the green one on the left side. We can choose that arbitrarily because it's the complete graph. It's no difference which vertex we choose. So we just choose the vertex labeled 1 or any. We set that as informed, and then we perform a round of push. That is, every informed vertex chooses uniformly at random one other vertex and pushes the information along. Here, maybe in that instance, the upper vertex over there is chosen and the information is pushed. And then we repeat that process until everyone is informed. So in the second round, we have now 2 informed vertices. They independently and uniformly at random choose a different vertex, push the information along, and then we do another round, maybe like this. And after 3 rounds, everyone receives the information, and then we stop. So we perform as many rounds as needed to spread the information to all the vertices in the graph. And the main question that we want to investigate in this model is how long does it take for the rumor to spread? So how many rounds do we have to perform until all vertices are informed? And the random variable that describes this property is called the runtime. We denote it by xn, and that's the number of rounds of the push protocol on the complete graph that we need to spread the rumor to all nodes. And of course, this is a random variable because we always randomly choose a neighbor and pass the information along. So to give you some intuitive understanding, we have two very distinct phases. At the first, when there are only very few nodes informed, so we start maybe picture 1 or 2 or 10 vertices. So if we uniformly at random select a vertex in the graph, we could just also randomly sample one vertex in the graph, and the probability that we hit one vertex that was already sampled before or that is in the set of informed vertices is very small. In particular, if we think at the birthday paradox that says if we have less than square root of n being the number of our vertices, if we have less than square root of n picks or samples, then the probability that we sample one vertex twice is small. It goes to 0 with n going large. So at the start, the probability that we pick a vertex double is very small. So at the start, we will be almost sure to never pick a vertex twice. So in the beginning, we have a doubling behavior. So the number of informed vertices doubles every round. If we have until square root of n, that is really surely doubling. But after that, we can say it's okay, it almost doubles. There is some small error, but still the number of collisions is very, very small because, well, the probability to hit an already informed vertex or to hit a vertex that someone else also hits is very small. And so intuitively, at the beginning, it doubles. And that means if we double all the time and we want to get to about epsilon of n informed vertices, so a small fraction at the beginning, then we have this logarithmic to the basis of 2, so the 2 logarithm of n and some constant term. So there's the term that I want to focus on is the log to the basis of 2 of n. So that's the first term that plays a major role in this protocol. And the second term that's important for the runtime, that happens at the end. So now we think about a lot of vertices being informed, maybe all but an epsilon fraction. And then we think, okay, how many pushes do we have to perform until we get to the last vertices? And the intuitive understanding that helps here is thinking about the Coupon collector problem. So choosing one neighbor uniformly at random is like sampling one vertex from the graph at random. And we know from the Coupon collector problem to get how many coupons do we have to draw until we draw each coupon at least once. And drawing a coupon at least once in our setting means that we pass the information to that coupon once, and then after that, if we pass it once, it's informed. So drawing it in the coupon collector problem once means it is informed. So if we have here a epsilon n fraction of vertices that we want to inform, we need to it's the same as drawing the last epsilon n coupons in a n coupon collector problem. And in the coupon collector problem, we know how many coupons we need to draw to get the last epsilon n coupons. That's n times the harmonic series of 1 minus epsilon n coupons. But this is the number of coupons drawn, not the number of rounds that we actually want to know. So we have to now relate this number of coupons or the number of pushes, so connections between individual nodes. We have to relate that now to the number of rounds, but as we are in the end, where there are all but a few vertices informed, we can just say, okay, we have n informed vertices, we divide that by n, and then we have that we about need natural logarithm plus some constant. So the harmonic number of n is natural logarithm plus gamma constant plus some lower order terms. So what we're interested in is the natural logarithm. So intuitively, in the beginning, the number of informed vertices doubles. Then we have some intermediate round, and at the end there is this Coupon collector problem. So in the first we need log to the basis of 2 of n, and in the end we need natural logarithm of n. And those are the highest order terms that we have. And this behavior was also observed in the previous works. So at first, where this model was introduced was in 85 by Alan Fries and Geoffrey Grimmett. And they also got this behavior that they say, okay, with high probability, so with probability going to 1 as n tends to infinity, the runtime is logarithm basis of 2 plus the natural logarithm plus some lower order terms. This then was improved by Boris Pittel in 87. He improved that lower order of logarithm, natural logarithm of n to a constant term. So he said, okay, it's actually only a constant that's added to the logarithmic terms. And he also gave some large deviation bounds. And the best result so far, and the most recent, is by Benjamin Durr and Marvin Kuhneman in 2014. They got lower and upper and lower bounds on the distribution. And from that, they derived some really sharp bounds on the expected value of the runtime that is up to constant additive terms with maybe difference 5 or 6. And our goal in this talk is to improve those bounds and to get the asymptotic runtime of push on a complete card as precisely as possible. And we more or less managed to do that as well. So what is our main result? What do we do need for that one property that we say that is a Gumbel distribution? Because in the Coupon collectors problem, we have the expected runtime to be about n times the harmonic number of n, and we also know that the deviation from the expectation is given by a Gumbel distribution. So that's why we also have a Gumbel distribution in our limiting distribution. But as we are not, or as we are in a discrete setting, so we only have a discrete number of rounds, we need a discrete version of the Gumbel distribution. So we denote by dgum from some parameter alpha the discrete version of a Gumbel distribution. So it has the same distribution function, but we only admit integer values. And with that, we can state our main result. That is, we take some parameters x and y, real numbers between 0 and 1. And then we need a proper subsequence of the natural numbers. I will say to that a little bit later. And then we know that the runtime on that subsequence normalized with the two logarithmic factors that we saw all the time, they converge to a Gumbel distribution with those parameters. And the astounding feature that we have here is that the convergence is only convergent on these two subsequences. So it's not convergent on an arbitrary sequence of increasing natural numbers, but only on those subsequences where the fractional part of the 2 logarithm converges to some x, and the fractional part of the natural logarithm converges to some y. And a priori, it's not even clear that such a sequence exists. But actually, we proved that it indeed exists, and that's one reason for that is that we can arbitrarily closely approximate real numbers by rational numbers. That's the main ingredient why this sequence has to exist. And on that subsequence, then we have a converge. So we have a local limit theorem only on a suitable subsequence. And in that distribution here, we have this mystery function C. And I want to show you that function C real quick. It looks like this. So this function C here in the discrete Gumbel distribution is a continuous function. It's periodic with periodicity 1. And it has a really, really small amplitude. So it has 10 to the minus 10 amplitude. And we could, the function C is only given as a double limit function of some iterated continuous functions. And we couldn't really get any more information out of it as than plotting it and showing that it's continuous and periodic. So it's a really weird function that creeps up in here. And with the convergence on the appropriate subsequence, we can also compute the expectation, because from previous works, namely from the work of Boris Pittel in 87, we know that the random variable x and I on this subsequence normalized with the logarithmic factors, it's uniformly integrable. So convergence in the distribution or in probability implies already convergence of the means, so we can easily compute the expectations. And so the expectation of that here is just the expectation of the discrete Gumbel distribution. We call it the function x h of xy, and it looks like this. So also the expectation in the end has this fluctuation that we had here in the distribution function. So maybe a bit astounding, as the previous works suggested that it's logarithm of to basis 2 plus logarithm of basis n plus some constant. And we now showed it's actually not plus some constant, but plus some very small bounded function. So the function has an amplitude of about 10 to the minus 4, then has an additional additive term of plus 1.182. So actually, we can say that, so this is as summarized, again, the result, the convergent distribution, and the expectation given up to small o of 1. And the summary in the form that Dörr and Kühnemann gave it is that we can now get this additive term that they had of -1 and +2. We can give it up to the 4th decimal place. And actually, this is tight. So these decimals can't be improved because we showed that there is a function in the expectation that is fluctuating in the order of 10 to the minus 4. So these constants are tight, they can't be improved. And this is, well, it's actually not a constant, there's a function there that's fluctuating on in the logarithmic scale and the logarithm to the base of 2. With that, I thank you for your attention, and if you have any questions, please feel free to ask them.
Simon, for the talk. So if anybody has any questions, we still have time for that. Remember to go to the microphone in the middle of the room. So maybe you should change that inequality for an approximately an equality almost.
Yeah.
I have a question.
Okay, great.
Okay, so yeah, very impressive that you can do such a detailed analysis. So do you think you can do the following? So let me add another parameter. It will be a probability p that whenever a vertex will just decide not to contact anybody, essentially, with some probability. Okay. Just
so like message transmission failures.
Yeah. And let's assume this probability not counting, it's fairly high, we're fairly close to 1. So the process will not be concentrated that much, because initially at the very start and at the very end, it will matter whether you succeeded or not. But like in the middle process, things should run kind of smoothly. Do you think you can do an analysis so precise, or with at least constant terms as a function of p for the logarithms?
I guess you can do something, because in the middle, yeah, it's really well concentrated. It follows really a deterministic recursion. So in the middle, there shouldn't be any problem. The beginning, where we have much more randomness. So it's the doubling. So maybe there is, we will have a distribution function in the beginning, I guess, like, because now the randomness only really happens in the end. So in the beginning, it's just doubling, then it follows a deterministic recursion, and then there is this random variable at the end. And if you have a probability at the beginning, maybe it's much more harder to track it if you have the random variable at the beginning as well. You have to keep track of it through the whole process. And I don't know, maybe it sure would be interesting.
Okay. Thank you.
Again, thank you for the talk. If anybody have any more questions, you can talk with Simon later in the break.
Thank you.
Thank you, Simon.